How does robot kinematics create our movements? Have you ever wondered how robots can move their arms so precisely? The answer lies in a fascinating area of study known as robot kinematics. This branch of robotics focuses on the motion of robot arms without considering the forces that cause that motion. It provides a mathematical framework that helps determine where each part of a robot arm should be based on the movements of its joints. This is essential for achieving controlled and accurate arm movements. At the heart of robot arm motion are two main concepts: forward kinematics and inverse kinematics. Forward kinematics takes the known angles of each joint and calculates where the arm's end effector, which is the tool or hand at the tip of the arm, will be positioned in space. Essentially, if you know how each joint is angled, you can figure out where the arm will reach. Inverse kinematics does the opposite. Given a desired position for the end effector, it calculates the necessary joint angles to achieve that position. This allows robots to move their arms to specific locations in their workspace. Robot arms consist of rigid links connected by joints, which can be either revolute, meaning they rotate, or prismatic, meaning they slide. Each joint provides one or more degrees of freedom, and the arrangement of these joints creates a kinematic chain. By controlling the angles or positions of these joints, the robot can change the arm's configuration, enabling it to perform complex tasks like reaching for, grasping, or manipulating objects. A common method to describe the geometry of these joints and links is the Dynavit-Hartenberg parameter model. This model simplifies the calculations for both forward and inverse kinematics. In practical terms, robot kinematics allows for smooth and accurate arm movements. For instance, when a robot needs to pick up an object, inverse kinematics determines the joint angles required to position the gripper at the object's location. Motion planning algorithms then create paths for the joints, taking into account limits and obstacles, ensuring the arm moves safely and effectively. Additionally, many robot arms use sensory feedback, such as vision and for sensors, to adjust their movements in real time. This sensory input helps refine kinematic calculations, allowing the arm to adapt to changes in its environment or the objects it is handling. This adaptability improves the precision and reliability of the robot's actions. In essence, robot kinematics creates arm movements by mathematically linking joint parameters to the spatial position and orientation of the arm's end effector. Through the use of forward and inverse kinematics, along with motion planning and sensory feedback, robotic arms can achieve the precise and flexible motions needed for a variety of tasks, from industrial assembly to delicate surgical procedures.